Let me hit record, you share. In the like in Chem 1, in materials, Unit 6, it's at the end of like the stuff from last week, but it's paper. It says, I'll show you what it says at the top. I got the mic. It's like this thing. It says balancing equation practice number 1. You know what I mean? And it's got some stuff about like concepts for balancing equations, and there's some reactions to balance. So you got more people coming in. That thing. Anybody need it? You got it? Yeah. Yeah. Let me look. Well, I don't, you would have had to actually like do it during class. I didn't read any of those. Okay. I got some more though. This is all the chem stuff. Just sort of got it organized. It's a mess too. It's not that one. Let's see. I got them back and forth, so they're like this. Where did it go? I can take. I just had it. I can just take notes on it. Yeah, I have. I can print some out. Let's see, balancing equations. I'll grab it. Printer's like in the back room. Else? It's weird. All right. Okay, so the first part is like kind of a conceptual thing. There's sort of multiple things for each, but not really. But this whole thing is about chemical equations. So some kind of a chemical equation, or you might write like a chemical reaction, whatever. Well, really chemical equation, or skeleton equation or something. Hold on, I gotta switch to a different thing. And 2 people are coming in too. It'll be so nice when school gets back to normal. I don't have to like, I hope school gets back to normal some year. You know what I mean? Zooming people, letting people in and whatnot. So chemical equations tell the story of a chemical reaction. Reactants are what we call the starting substances, and products, those are the new substances that are formed. Large numbers in front of some of the formulas are called coefficients. Just like a coefficient in an algebraic equation. These numbers are used to balance the equation because chemical reactions must obey the law of conservation of matter. Sometimes it's called the law of conservation of mass or conservation of matter. It could be matter or mass. You know, the definition of matter is anything that has mass and volume, mass and takes up space. What's up? Yeah. one here if you need. So it has to have mass. So law of conservation of mass, law of conservation of matter, they really mean the same thing. Numbers of atoms on, you need both of them. On both sides of the equation must be equal, or you say balanced, because matter cannot be created nor destroyed. When balancing equations, the only numbers that can change are coefficients. You know, if you change the subscripts, remember that subscripts, they can never be changed. If you change the subscript in a chemical formula, it changes what chemical it is. So there are chemicals that seem like they're the same, but maybe have different subscripts. Like, I don't know, we already talked about like CO, that's carbon monoxide, but CO2, that's carbon dioxide. Or water is H2O, but hydrogen peroxide is H2O2. So if you were to change the subscript to help balance the equation, that would completely change what chemical is present. We're not talking about changing what chemical is illustrated, but trying to change what the coefficient is in order to balance the number of atoms that have to be present. That's the fundamental principle of balancing equations. Sound cool? All right. So here's the deal. We'll go through the other ones. We'll go through and balance these. If you already did them, you can just double check. But if you didn't do it, or if you are confused and you want to see like the method, I'm going to work through the method for 1, 2, 3, 4, 5, 6. And it's actually 7, 8, and 9, but LOL instead of saying 9, it says 10. It's because, I don't know, you know, like Word, you ever like number stuff in Word and it changes the numbering and you just can't stop it? You know what I mean? You're like, stop doing that. And then it just keeps on going. I don't know. So it was probably auto numbered and then manually numbered or something like that. Okay, so Al plus O2 is Al2O3. This is the oxidation of aluminum. Aluminum, when it's exposed to air, will oxidize. It'll make aluminum oxide. And this is a common form that we find it in the earth. So there's one aluminum on the left, but there's two aluminums on the right. So just analyzing it atom by atom, you can just do that first and say, well, I got one aluminum on the left, there's two aluminums on the right. So if I put a 2 in front of this Al, now there's two aluminums on the left and two aluminums on the right. And then there's this oxygen, which is O2. So there's two oxygens on the left, but there's three oxygens on the right. Well, the number of oxygens you're going to have on both sides is going to be the least common multiple of 2 and 3, which is 6. So it's going to have to be 6 oxygens on the left and 6 on the right. So in that case, you'd have to put a 3 in front of the oxygen and then a 2 in front of the Al2O3. But what you got to always double check is, did putting a coefficient in front of something affect the balancing of something else? So by putting the 2 in front of the Al2O3, now that has 4 aluminums on the right, but there's only 2 on the left. So that 2 is actually not correct. That had to be 4. So 4 aluminums and 3 oxygens make Al2O3. Let me show you another way to deal with that one, or to deal with this idea. So I showed you before, you can make a list of the elements that are in the reaction. There's aluminum and there's oxygen. And then if you make a list, this is of what's starting. There was 1 aluminum, and then there were 2 oxygens. These are the reactants. And then for products, there were 2 aluminums and 3 oxygen. A little hint is, if by comparing the number of reactant and products for each of the elements, you have something where the least common multiple is going to require you to multiply both of the value, both of them by something, then you should balance that one first. What I mean by that is, for the aluminum, there's 1 reactant and 2 products. So all you'd have to do is put a 2 in front of the aluminum. But for the oxygen, because there were 2 oxygens on the left and 3 oxygens on the right, you can't balance oxygen by just putting a coefficient in front of one of the compounds containing oxygen. It turns out you have to put a coefficient in front of both compounds containing oxygen. So here's what I'm saying by that. If you do it by, this is a kind of a quicker way to balance equations, Al2O3. when you look at, see how many reactant and product of each of the chemicals, because oxygen is going to have 6, so that there's 2 oxygens on the left and 3 oxygens on the right to start with, you're going to have to end up with 6 on each side. Balance the oxygens first. And by balancing the oxygens first, you put a 3 here and you put a 2 here. And then when you balance the aluminums, 2 times 2 is 4, you can just put a 4 here. So instead of going in order, you sometimes have to like fix one. You can look to see which of the chemicals is going to require a coefficient in front of both places, because the least common multiple is a multiple of both of the values. I'll show you other places where you can see that too. Like for instance, in the C3H8 and oxygen, this is propane. So if you have a propane grill, you're burning propane. Propane and oxygen make CO2 and H2O. It's a combustion reaction. If you list, oh yeah, and this is a synthesis reaction. Anyway, this is propane. If you make a list of the chemicals C, H, and O, and make a list of how many of each, there were 3 carbons on the left, 1 carbon on the right. There's 8 hydrogens on the left and 2 on the right. And then there's 2 oxygens on the left and 1 oxygen on the right. In this case, the 1, 2, oh, I'm sorry, this is 3, because there's 2 oxygens here and 1 there. In this case, carbon is evenly divisible by 3. These 2 hydrogens are evenly divisible into 8. But this oxygen, see how you got the 2 and the 3? There's 2 oxygens on the left, but there's 3 on the right. You want to deal with that oxygen first. But this is a tough one, because you kind of get a feeling you're going to have a 3 here, but there are so many ways to end up with 6 oxygens on the right. It could be you don't put anything here and you put like, I don't know, 5 there, or you could put like a 2 here, and then you're going to need like 2 there, or you could put, or let's see, I don't know, put a 2 here and a 2 there. You put a 3 here. We can't put a 3 here because that's just not right. So this one might be a little bit tricky, but you could just start with the carbons if you want. So if it's not clear as to which one you start with, it kind of doesn't really matter. You get a sense of how this all goes. You got 3 carbons on the left, so you need 3 on the right. You put a 3 here. And that now fixes the carbon, but it also changes the oxygen to have 6, because there were 3 in front of the CO2. And then the hydrogen has 8 on the left, and you're going to need 8 on the right. So if you put a 4 in front of the water, that changes the hydrogen to 8, fixes the hydrogen. And now the oxygen, because there's going to be 6 here and 4 more there, now there's 10. So it turns out that to balance the oxygens, it's not even that you would put a 3 in front of here. It's actually going to have to be a 5 in front of here. So altogether, you got 3 carbons on the left, 3 carbons on the right, 8 hydrogens on the left, 8 hydrogens on the right, 10 oxygens on the left, and then 10 oxygens on the right. So it goes nothing, and 5, 3, and 4. And that's a combustion reaction. You can tell it's combustion in a bunch of different ways. Generally, in combustion reactions, you're burning something containing carbon and or hydrogen in oxygen to produce carbon dioxide and water vapor. All right, number 3, you got this aluminum nitrate and sodium hydroxide, make aluminum hydroxide and sodium nitrate. Here's a trick with double replacement reactions. You see how there's oxygen in the nitrate, and there's also oxygen in the hydroxide. A smart thing to do is to identify that there's this NO3 on the left. There's also an NO3 on the right. There's also an OH on the left and an OH on the right. So don't try to balance like oxygen atoms separately. Instead, think of those ions as being like little chunks, because the NO3 is the same NO3 on the left as it is on the right. And this OH is on the left, but there's also an OH on the right. And you might even see real quick that there's always 1 aluminum on the left, 1 aluminum on the right. There's 1 sodium on the left, 1 sodium on the right. The only thing that's a little bit different is there's this NO3 with a 3 after it, and then there's an OH with a 3 after. So the only thing that you're really balancing to start with is the nitrates and the hydroxides. Because there's 3 nitrates on the left, if you put a 3 in front of the sodium nitrate on the right, then the nitrates are balanced. And then here, because there's a 3 after the hydroxide, if you put a 3 in front of the sodium hydroxide, then that balances the hydroxides. And that's all you have to do. Because now you've got 1 aluminum on the left, 1 aluminum on the right. There's 3 nitrates on the left. Now you've got 3 in front of the sodium nitrates. There's 3 nitrates on the right. There is 3 in front of the sodium, and there's also 3 in front of this sodium. There's a 3 in front of the hydroxide, but you got 3 hydroxides. So when you see polyatomic ions, don't try to balance the individual atoms, but try to balance the polyatomic ions, because the NO3 isn't going to change to NO4 or something like that. The OH isn't going to change to like O2H or OH2. It's just going to stay as like an OH. That's a double replacement. Double replacement. Cool. Questions, thoughts? It's kind of fun and easy once you like do a bunch of them anyway. All right. So there's oxygen, carbon disulfide makes carbon dioxide, and sulfur dioxide. So in this one, if you make a list of the elements, there's oxygen, carbon, and sulfur. On the left-hand side, there were 2 oxygens. On the right-hand side, there's 4 oxygens. For carbon, on the left-hand side, there's 1 carbon. On the right-hand side, there's 1 carbon. And for sulfur, on the right-hand side, there's 2, or left-hand side, there's 2. On the right-hand side, there's only 1. So it looks like you got to double the number of oxygens on the left. So if you put a 2 in front of this O2, now there's 4 oxygens on the left. But the sulfur is not balanced. So if you put a 2 in front of the sulfur dioxide on the right, that doubles the number of carbons, but it also increases the number of oxygens to 6. So it turns out that that 2 in front of the oxygen wasn't right. That 2 has to be a 3. Now you got 6 oxygens. So in number 4, you got to end up with 6 oxygens on the left, 6 on the right. Always be careful to look that, for instance, in this one, there's oxygen in 2 different compounds. There's oxygen both in CO2 and the SO2. 1 carbon on the left, 1 carbon on the right, 2 sulfurs, because there's a 2 after the sulfur on the left, and then a 2 in front of the sulfur dioxide. So you got 2 sulfurs on the right. So KClO3 goes to KCl and oxygen. That's a decomposition reaction. I didn't ask about reaction types, but this is not exactly, this isn't even a, this is not, it's sort of a synthesis. It's kind of a decomposition. It's not, doesn't neatly fit into one of the categories. It's not really a single replacement either. But this is clearly a decomposition reaction. KClO3 makes KCl and oxygen. The only thing that's not balanced to start with is the oxygen. But there's three oxygens on the left, 2 oxygens on the right. So you put a 2 in front of the KClO3 and a 3 in front of the oxygen. That balances the oxygens. But now you upset the KCl. So you need a 2 in front of the KCl on the right. So now you got 2 potassiums, 2 chlorines, and 6 oxygens on both sides. And 6, you got barium fluoride, potassium phosphate, make barium phosphate, and potassium fluoride. Again, look at the polyatomic ions. This one's actually not confusing because it isn't that there are 2 polyatomic ions containing oxygen. But if you see there's this PO4 and there's a PO4, deal with it as that it's PO4. And because there's a 2 after the PO4 on the right, you're going to need 2 of these PO4s. So if you put a 2 in front of the potassium phosphate on the left, then that fixes that PO4. The barium's messed up. There's 3 bariums on the right, so you're going to need 3 bariums on the left. And then it turns out it's actually pretty neat because there's a 3 in front of the barium phosphate, so that gives you 6 fluorines, or barium fluoride. So you have 6 fluorines, and there's a 2 in front of the potassium phosphate, and this potassium has a 3 after it. So 2 times 3 is 6 um, potassiums. So there are 6 fluorines and 6 potassiums, but on the right, there's only 1 potassium and 1 fluorine. So you got to have a 6 in front of that. So in order to make any of these reactions happen, that's the correct ratio of the compounds. Every reaction that we do in the remainder of this course, we got to get these ratios right. You got to have like 3 barium fluorides and 2 potassium phosphates, and only when that 3:2 ratio is right, then you always make exactly 1 barium phosphate and you get 6 potassium fluorides. And what else is true in chemical reactions is maybe we're trying to make this. This is like our desired product. But this we also get. This is like some other side product or waste product. In this reaction, it would be very unfortunate because you're trying to make barium phosphate maybe, and every barium phosphate you actually make, you get 6 of these potassium fluorides. You got to figure out what to do with them. Maybe you can sell it to somebody. Maybe you can do another reaction with it. Back in the day, we just used to take those things, just dump it in the ground, throw it in a river. But now we're careful about the way in which we dispose of stuff. But most of the time, there's some kind of a practical use for some new chemical that's formed. People call this like a side product. Like I mentioned about that chemical plant down in Mill Hall where they extract stuff from olive oil, but they also get this gooey mess left over, and that side product is what they use to make Post-it note adhesive at the factory next door. All right, then 7, 8, and is actually 9, but 10 or whatever. Again, look at the polyatomic ions. You see there's this SO4 and an SO4, and then on the right or left there's this nitrate, NO3, and there's an NO3 on the right. So deal with balancing the chunks of stuff, not the individual atoms in this case. There's 2 hydrogens on the left, so you need 2 hydrogens on the right. So you put a 2 in front of the HNO3, and that fixes the NO3 because now there's 2 in front of the NO3 on the right, and there's a 2 after NO3 on the left. That's it. It's done. Sometimes you can get by with just like 1 coefficient. Sometimes you got to like put coefficients in front of everything. Sometimes only in front of a few of them. Same with like number 8. You see there's this SO4 on the left, but there's 3 SO4s on the right. So that I pick out in my eye right away is that these 3 SO4s on the right, but only 1 on the left. So if you put a 3 in front of the H2SO4, that fixes the sulfate. Another little trick is if there's an element that appears by itself in the reaction, do that last. Meaning, like, because there's aluminum as a separate element and hydrogen as a separate element, do those last. And the reason why you want to do those last is because you could put any number in front of this aluminum and fix aluminum. Like, any integer will work. But you see, different integers in front of aluminum sulfate, because every sulfate comes in 3s, it's either going to be like 3 or 6 or 9. You get all kinds of different numbers. So when there are individual elements, try to do those last. So you got 3, this is sulfuric acid. Well, it's aluminum and sulfuric acid make aluminum sulfate and hydrogen. On the left, there was 1 aluminum. On the right, there's 2. So you got to put a 2 in front of the aluminum. And here there's 3 H2s. So it's going to have to be a 3 in front of the H2 on the right. And that one's done. Okay, 10 is a cool reaction. W, that's an element symbol you haven't really seen much. That's tungsten. The symbol for tungsten is a capital W. In German, it's Wolfram, or Wolfram, which is probably the coolest element name in any language. and that's why it's W. Um, Light bulbs, like incandescent light bulbs, like old light bulbs with the filament inside a light bulb was made of tungsten. Tungsten is a fairly rare element, but the good thing is you don't need much of it to make a filament. But tungsten isn't found as a element by itself. And also, when light bulbs operate, the inside of the bulb has to be evacuated. There can't be air inside there because tungsten reacts with oxygen to make tungsten oxide. And that's what causes the light bulb to burn out. If oxygen gets into the bulb, then the bulb will blow. So this tungsten oxide, WO3, that's the oxide of tungsten. So tungsten has the highest melting point of all metals. That's why it's also chosen to be filaments in light bulbs, because you pass huge amounts of electric current through it and get that wire to be stupid hot, and then it gives off tons of light, and it doesn't melt. But what causes the filament to eventually blow is any kind of oxygen that gets in there causes tungsten oxide that actually falls off, and that's what makes the inside of light bulbs. It coats the inside of light bulbs. The light bulb might start off nice and bright white, and then it gets kind of like a grayish color, and that's because the tungsten oxide ends up evaporating and going to the surface of the glass instead of like on the bulb itself. It's the same with like headlights for cars use they call them halogen bulbs, but there's a tungsten filament, and the gas that fills the bulb is a halogen. So they're fluorine, chlorine, bromine, or iodine. That's what it means to be a halogen bulb. Is they put one of the halogens in. Anyway, so you got tungsten oxide and hydrogen make tungsten and water. It doesn't matter which one you start with here, but there's one tungsten on the left, one tungsten on the right. There's 3 oxygens on the left. There's only 1 oxygen on the right. So it looks like you got to put a 3 in front of the water. But and then you got hydrogen to do, so you got to have a 3 in front of the hydrogen. So there's 1 tungsten on the left, 1 tungsten on the right, 3 oxygens on the left, 3 oxygens on the right, and then 6 hydrogens on the left, 6 hydrogens on the right. So that's how those go. Okay, now you don't write ones in front of the chemicals. In other words, like it's redundant and unnecessary to put ones in front. So don't really do that, except unfortunately, there's kind of no way around that in like Schoology things if you do it as like a submitted thing. So let me show you this. Share. That came up right. All right, so in the current unit, Unit 6, you find a folder for this week. Week of 125 to 129. And I'm going to add more stuff in there, but it says schedule for the week. One of the problems I gave you on Friday. And then there's a balancing equations homework in the upcoming list. This link should take you there. So it's either there, or you can just look at it on the right-hand side. But in your, what a pain, go back. In your upcoming list, there should only be one thing. And it says, like, balancing equations homework. And I made a note. I wish this were just a little bit faster. I made a note here in that Schoology assignment, even though you don't include the number 1 as a coefficient chemical equation, the Schoology assignment can't accept blank spaces. If you put a blank, it doesn't do anything. So what I mean by that is whenever you're doing this thing in Schoology with balancing the equations, like here, Bryson already did it. It's like Na3PO4, KOH, NaOH, K3PO4. When you're doing it, you've got to actually put a 1. If you leave a blank, it will just say you get nothing. You know what I mean? So don't normally put a 1. But in your Schoology, there's 5 to do, and those 5 to do, you got to actually put a 1 in the space. We're trying to find another, I don't know, there's just so much to do this year. Try to find another way in Schoology for it to like accept. The problem is if you leave it blank, it counts it like as a 0. You know what I mean? Yeah. I still go back and double check. I know it's like a meme where people will like put like the right answer, but then it says it's not the right answer. And it could just be because the acceptable answer like might be capitalized or not, or something like that, you know, as an obnoxious thing. So the ones that it's kind of sketchy, I always double check to make sure that like it's actually working right, or you're actually putting something in that's good. I look through all the answers. So Schoology auto scores a bunch of stuff, but in that one, because there's multiple things to put in, you can't have multiple options for multiple things for the same question. It'd have to be separate questions for each of the spaces. Then you can have multiple options, but you can't have multiple options for a problem that has multiple parts, because those multiple options are like interchangeable with each other. I don't know. I didn't invent Schoology. It's just the way it behaves. We tried a bunch of stuff last night. But there's a investigating reactions lab on Wednesday, and then the thing about chemical reactions is not all reactions actually happen. Just because you write 2 reactants doesn't mean that products will form. Like if you take iron and put it into water, it just gets wet. It doesn't, there's no reaction. It doesn't happen. It doesn't like some new chemical forms, you know? If you take like in the air in this room is nitrogen and oxygen. And the nitrogen and oxygen, they don't react with each other. They're totally non-reactive. But oxygen does react with a whole bunch of different other stuff. So I'm going to show you how to determine and predict whether or not reactions take place. And then some chemical reactions produce like solid precipitates, where other times the reaction product is not a solid, but it stays as like an aqueous substance. I don't know. So you can do that now if you want. There's like 13 minutes left or so at balancing equations. If you have other questions or you're still like working through it, another thing that you can do is we've been writing equations for a few weeks. You can go back to any paper you've got or anything that we've done that has chemical equations and try practicing them. I have some additional practice ones I can give you tomorrow in case you want to like do some more. But once you get it, then you got it. And that's a skill you have. Then you'll know how to balance equations the rest of your life. But if you're still having trouble, I can still help you. Yep. Yeah, you can just keep it like as a, you know, yep.